Okay, the last thing we're going to hit on in these two chapters is the generalized Hooke's law for isotropic materials. Now, like I said earlier, we have these situations and we're being pulled from three different directions, which if we think about it would cause three different ways of it straining in all three directions. But how are those going to affect each other? Because we know that if it strains in the x direction, it gets smaller in the y and z directions. Or if it strains in the y direction, it gets smaller in the x and z directions. So all that is going to be combining. So we're going to have to figure out how we can do this. And it's actually not too terrible because we can use that magical superposition principle thing to get us through it. So let's talk about the superposition principle and how it helps us. So the full derivation of how it gets together can be found in your book. But the biggest thing is simply saying you're more or less adding all of the strains together. So all the strains from all the stresses, and you say, okay, when I've done that, what does it look like? And as a note here, where you see A, B, and C, it can be replaced with either X, Y, or Z respectively. Just don't put X in place of every single one of the letters. You can only put X in place of A, or X in place of B, or X in place of C. It's just a lot simpler to write down these equations twice than to write down 6 equations, one for each the X, Y, and Z, since they're identical. And another thing you might be wondering is, what about shear stress and shear strain? But luckily, those are all independent, so we don't actually have any special equations there. Now, I will take a moment just to show you where this comes from, and then we can move on. So first off, we know that stress in the x direction is equal to strain in the x direction is equal to our stress in the x direction over the modulus elasticity. And we can continue that for y and for z. We also know that when I have a strain in the y direction, well, that's going to be causing a strain in the x direction as well. A strain in the x direction as well. So how much strain in the x direction? Okay, how much strain in the x direction? Well, let's see if we can figure that out. So first off, this is going to be proportional to sigma y over E. Okay, and so that all works out fine. But now let's use our Poisson's ratio to figure out the next part. So Poisson's ratio is going to be equal to negative, and then it's going to be the strain in the other direction. So in this case, we'll just say negative strain in the x over strain in the y. And make sure that I always want to mess this up. I'm trying to do the derivation, so I think I'm doing good so far. Yes. So as the strain in the y increases, the strain in the x direction will increase, but it's going to be getting smaller rather than bigger, or vice versa. Okay, now I'm going to solve for the strain in the x direction, because that's what's going to matter in the end. So I do that, and I'm going to get that the strain in the x direction is going to be equal to negative my strain in the y times Poisson's ratio. And then I can further plug that in terms of stresses rather than strains, and so it's going to be equal to negative sigma y times Poisson's ratio over the modulus elasticity. And so when we add all of these together, this strain plus this strain plus the one I could also get from the z axis as well, you end up with this equation, where this term right here, that's turning into this. So hopefully that makes sense. We're just adding together all the different strains from all the different situations and solving. And we can also do that in the reverse order, where we solve for the stresses in terms of the strains. Both is going to be helpful in the future. So that's for this time. Now we're going to jump into some example problems. So thank you for listening, and I'll see you all later. Bye-bye.